In this video, we're going to continue exploring the concept of implicit differentiation. And this is part 2 of our video series for that topic. So here's an example. We know the area of a circle is A equals pi r squared. Now imagine that you throw a pebble in a lake. The pebble creates a circular ripple effect in the water. As seconds pass, so as time is passing, think about what is changing in the circular ripples. So I gave you like a little head start. I said I can think of 3 things. Can you list at least 3 things that are changing as time passes? So go ahead and pause the video if you need to think about it, but if you already thought about it, then continue on. So what are some things that are changing right as the ripples start going and going and going? So some things that change are the radius of the circle. So that's one. So we can say the radius of each circle. Right, they're circular ripples, so the radius of each circle is changing. And so this means that since the radius is changing, what else changes? The area will be changing, and the circumference will also be changing. So each ripple, as time passes, right, it gets bigger and bigger and bigger. The radius is changing, the area is changing, the circumference is changing. And so how can we incorporate the concept of implicit here? So things are changing. The radius, the area, and the circumference are changing. And what is it? How do they change? They're changing with respect to what? They're changing with respect to time, right? So that means that for this particular example, the area of the circle will be a function of time. So area is a function of time, and so is everything else. The radius and the circumference are also functions of time. So looking back at our area formula that I wrote up here, we have A equals pi r squared. Now this kind of leads you to believe that A is a function of the radius. Right here, A equals pi r squared, but now as we say, as seconds pass, what the things that are changing are the radius and the area. So both of these are actually functions of time. So I could rewrite A equals pi r squared. Since they're functions of time, I could say then A of t is equal to pi r of t squared, because time is really the independent variable. As time changes, that's affecting how the area changes and how the radius changes. So this will be an example of how implicit things work. And notice that in this case, the variable, the independent variable, the t, is not even a part of the original equation to begin with. So this is a great example of how implicit can work. So let's try an extension of this problem. So after 3 seconds, if the radius changes at a rate of 0.25 inches per second, how fast is the area changing? So this is a bit complex, right? We have after t equals 3 seconds, if the radius changes at a rate of 0.25 inches per second, how fast is the area changing? So this is pretty interesting, because then we need some information. How fast? So this is, what am I looking for? I'm looking for a rate of change, right? How fast is the area changing? So we are looking for the rate of change of area. So how can you write that mathematically? Meaning, what will the notation be? So the rate of change of area will be the dA dt, because how fast, so the area is changing with respect to time. And we know if the radius changes at a rate of 0.25 inches per second, notice that this is also with respect to time. So the rate of change of the radius will be dr dt, because radius is a function of time, and we know that that's 0.25 inches per second. So when I have A equals pi r squared, then I would need to get my hands in the rates of change, so dA dt and dr dt. So that means that here I will take the derivative with respect to t, the variable t, which is not even in the equation. So that's what makes this slightly complicated and confusing, but I can still do that. So then I will say dA dt, right, the derivative of a with respect to t will be the derivative of the right side with respect to t. So pi is just a constant, so we'll pull it out. So it'll be dA dt is equal to pi times the derivative with respect to t of r squared. Now remember, r is a function of t, so it's kind of like if I have r of t squared. So this will be 2r times dr dt by the chain rule. And so this will be our derivative. Now, I did not give enough information in this problem because notice that I do have, well, we know that that is 0.25 inches per second. I would need the value of r in order to solve this problem. And we are not given the value of r here. We just know that after 3 seconds, the radius changes at a rate of 0.25 inches per second. We might be able to, based on the rate of change of the radius, be able to find what the radius is after 3 seconds. And so once we do that, we can plug that value of r in here, and we will find our dA dt. So I think we can do that fairly quickly, don't you think? So when t equals 3 seconds, or after 3 seconds, then the radius will be the 3 seconds, right, times the rate of change of the radius, which is 0.25 inches per second. So our seconds will cancel, leaving us with what is that? 3 times 0.25, which is 0.75 inches. So that will be the radius after 3 seconds. So and in 3 seconds, the radius has grown from nothing, right? There was nothing in the water. So when you throw that pebble and it starts increasing, so after 3 seconds, it's 0.75 inches. So now I could find the rate of change of the area. So the area will be changing at pi times 2r, so 2 times 0.75 inches times dr dt, which is 0.25 inches per second. And so notice that our units here are also inches. And so when you do this, what is that? 2 times, so multiply everything. Pi times 2 times 0.75 times 0.25 inches per second. Notice that our units are going to be inches square per second, which makes sense because inches square is a measurement of area. So the rate of change of area, so that is inches square per second. So that will be correct. So let's figure out what this number is. Pi times 2 times 0.75 times 0.25, which I get 0.375 pi inches square per second. And so that will be the rate of change of area. Now, this was an extension of implicit, but my main point here, and we'll evaluate problems like this later. This is a preview of coming attractions when we get to related rates problems, but this is an application of implicit, right? So what I wanted to show here is that when you have a problem like this with the ripple effect, you have the area of a circle, but both of the variables, the area and the radius, are changing with respect to a completely different variable, time. That's not even part of the equation. And so that makes this implicit really helpful and useful, and is used in economics quite a bit, because when you're looking at like profit, revenue, and demand, a lot of times things like that are changing with respect to time, and then or price of an item, right? Like everything is in economics, a lot of things are driven by price of something. So then the profit, the demand, and the revenue are changing with respect to the price of an item. All right, let's try a few more examples in this video. And for these, I'm going to alternate to the other notation, the y prime, just because sometimes it is easier to write. So find dy dx, also denoted y prime. So for these, now the one thing to be really careful here is when you see y prime or find the derivative of something, make sure that it's specified with respect to what variable. So in this case, dy dx is what y prime means. So I'm taking the derivative of y with respect to the variable x. So here I have y times tangent of x equals 2x squared plus 5x squared. Now I made a point to say y times tangent of x because remember, y is a function of x. So when I see y tangent x, what does that really mean? That means f of x times tangent of x. So how do you take the derivative of something like that? We need the product rule, right? So that's what we're going to use here. So when I take the derivative, I'm going to try to find y prime. The product rule then is going to tell me, so product rule on the left is the derivative with respect to x of the first times the second left alone plus now the first left alone times the derivative of the second. And then take the derivative of the other side as well. So the derivative with respect to x of 2x squared plus the derivative with respect to x of 5y squared. Now again, you don't have to write this step, but I'm trying to just be intentional as to what I'm taking the derivative of. So the derivative of y with respect to x, that's dy dx, or y prime. So I have y prime tangent x plus, now that's just y, times the derivative with respect to x of tangent x. The derivative of tangent is secant square of x. And notice that even if I wanted to use the chain rule here, I could. It will be the derivative of tangent, right? And then by chain rule times the derivative of the inside, which will be the derivative of x with respect to x. But this is just 1. So when I'm taking the derivative of the variable with respect to the same variable, then that derivative is just 1. So that's why you don't see it when it's x with respect to x. Equals the derivative of 2x squared with respect to x, so that will just be 4x plus, now here remember y is f of x, so this is like saying 5 times f of x quantity squared, so we need the chain rule there, so that will be 10y to the first times the derivative of y with respect to x, so times y prime. So I need to get everything that has a y prime on the same side. So here is personal preference. Which one do you move? So I'm going to move the 10y y prime over. And so that means I'm going to subtract it from both sides. So I'm going to have y prime tangent x, right? These are being multiplied. So y prime times tangent x plus y secant square x minus 10y times y prime equals just 4x. Now I need to get rid of this one, so move it to the other side. So I'll have y prime tangent x minus 10y y prime equals 4x minus y secant square x. And now that I have the y's on the same side, now we can factor it because that becomes a common term. I have two terms with a common factor of y prime. So factor out the y prime. I said we had two terms, so we should still have two terms on the inside. So what are those two terms? So I'm going to have tangent x minus 10y. And now we're ready to get y prime by itself. Divide both sides by tangent x minus 10y. So y prime is 4x minus y secant square x all over tangent x minus 10y. Now if I was trying to find the equation of a line tangent to the curve at some point, I need both the x and the y value in order to plug it in, because notice that now my derivative has both variables in it. It has x and it has y's. So I need both coordinates. Let's try the second example. Now on this one, same thing, find y prime. which means dy dx. So let's take the derivative with respect to x of both sides. So the derivative with respect to x of, oh, I have a quotient here. So that means we're going to need quotient rule. So let's work on the left. So derivative with respect to x of y cubed. So notice here, again, try to think of this as if you have f of x cubed. Y is implicitly a function of x. Anytime you're trying to ask y prime, ask to find y prime, which is dy dx, that means you're taking the derivative of y with respect to x. That means that y is implicitly a function of x. So how would you take the derivative of this, right? Then you need the chain rule is needed. So let's take the derivative. So that means I will do 3 times the inside left alone, and then to the 3 minus 1. So it will be y squared. Then by chain rule times the derivative of the inside, f prime of x, but my inside is just y, so y prime. Plus the derivative with respect to x of a constant, that's 0, equals, here we need the quotient rule. Oh, let me give myself more room here. Okay, so here we need the quotient rule. So quotient rule says bottom, so x plus y, times the derivative of the top, so times 2x, minus, is quotient rule, right? So minus the top, x squared, times the derivative of the bottom. So here the derivative of x with respect to x is 1, and the derivative of y with respect to x is dy dx, or y prime, all over the bottom square. Now this, when I want to solve for y prime, it creates more trouble than we've done in the prior examples, because I have y prime on the left and I have y prime on the right, but it's stuck on the numerator of this crazy thing. So let's simplify this by multiplying everything out and trying to combine like terms, if there are any. So here, what are we going to have? So 2x times x, that's 2x squared, plus 2x times y, 2xy. And now here, notice that I am taking my minus with me. So it's negative x squared into here. So minus x squared minus x squared y prime, all over x plus y squared. So one of the things to try to make this a little bit faster is I can separate the fractions into this numerator over this denominator, and then minus this part of the numerator over the denominator. I meant to use a different color there. This part of the numerator over the same denominator. So what I mean by that is, so I'm going to separate 2x squared plus 2xy minus x squared over x plus y squared minus, and then as long as I have the same denominator, I can split up fractions. Right, and the reason that I do that is because then I've separated the y prime term, but notice that I still have the same denominator. So if I wanted to put them back together, same denominator, combine the numerators, and I get the same thing. So now though, I get to add this term to the other side. So add it to the other side. So I'm going to have 3y squared times y prime equals, whoops, plus, I'm adding it, right? Plus that term that I'm adding. So plus x squared y prime over x plus y quantity squared equals the term that I left on the right side. And now I have two terms with a common factor of y prime. So take out the y prime and you're left with 3y squared plus x squared over x plus y quantity squared equals this mess. And now, how do you get the y prime all by itself? Divide by this. Now, if you wanted, you could get a common denominator here. That way, when you divide by this, you're dividing by a fraction, which means you can multiply this side by the reciprocal of that fraction. But here, I'm just going to say y prime is equal to 2x squared plus 2xy minus x squared over x plus y squared divided by, so this, I don't know that I made it look any pretty, 3y squared plus x squared over x plus y squared. Now resist the urge, you don't cancel those, right? Because that is not a common one to here. And that's where I mean that if you get a common denominator, right, if you have x plus y squared, then you will be able to cancel them. So then once you have the same denominator, you can cancel them because you'll have 2x squared plus 2xy minus x squared over x plus y squared over, and now you would have this 3y squared times x plus y squared plus x squared over x plus y squared. And now these guys can cancel. If you multiply by the reciprocal, you might be able to see that better, why they cancel. And so my y prime then will be the numerator of the top fraction divided by the numerator of that bottom fraction. 3y squared times x plus y quantity squared plus x squared. If you wanted, you can multiply this out, but ideally you would have a point given that you get to evaluate at, like x1, y1, and then you will plug that in and don't have to simplify as much. Sometimes it's easier with numbers. So if I was evaluating this at a particular point, I would probably plug in the point right after I take the derivative, like right probably over at this step, because then all I'm dealing with is numbers instead of having to simplify this crazy thing. So, but this will be a good way to leave your derivative simplified. All right, so that's part 2. Part 3, I'll do a couple more examples, finding an equation of a tangent line and also doing higher order derivatives, finding the second derivative of something like this.